see the context-free grammars problems. So if you have not watched my first video of first part of context-free grammars, I would recommend you to go through the context-free grammars first part. In the first part, I have discussed about the definition of what is a grammars and what are the different attributes of the grammars and how to do a simple derivations of the grammars. So this problem, like if you have to write a grammars for a power n, it is s tends to as. So this is going to be deriving any number of a's. Similar fashions, we have also seen like clean plus, that is at least n greater than or equal to 1 means at least one a should be there in the grammar. So that will be the one terminal. It is s tends to as, only one a will be terminated. So any string over sigma is equal to a comma b. So it is as, bs or epsilon, because it is a comma b the whole star. Any number of a's, any number of b's. S tends to as or bs or epsilon. So this is how you should be able to write it. Similar fashions, languages of a power n and b power n. So language is equal to a power n and b power n, where n greater than or equal to 0. It is a followed by b. Hence the grammar is s tends to a, s, b or epsilon. So this is going to be generating equal length of a's and b. That is a power n and b power n, wherein a followed by b. So here is the derivations. We can see that ASB, AASB. So ASB, whenever we want to terminate with an epsilon characters. Similar fashions, we have a problem on a power n, b power n, where n greater than or equal to 0. N greater than or equal to 0 means the terminator would be AB, because when you substitute n greater than or equal to 1, this is the minimum values that it can take. A power 1, b power 1, it is AB. Okay, ASB or AB. So this is how we should be able to generate. Similar fashions, here we have a power n, n plus 1, b to the power of n. So this can also be written like this. So let us go here and we will see. So here is a problem statement. So this can be written like this. This problem can be written like this. It is a power n and b power n, and a is 1 a is extra. So this is equal to a power n and b power n only the terminator will be equal to a. Similar fashions, if it was like a power n plus 2 b power n means it would have been s tends to, the solution for this one would be s tends to ASB and terminator would be AA. So because this can be written as a2 is a power n and b power n. So this is how the grammar should be generated for a power n plus 1 and b power n. Similar fashions, we have a few more other examples. We'll see that. Okay. So the next problem is some language of palindrome. So here is a palindrome series. So for the palindrome series, so it would be like this. The palindrome series, it is, the pattern would be something like A, B, B, A. Okay. So the first and the last symbol should be the same. Okay. So the palindrome should be whatever the character it takes, it should be ending with the same only. So it is ASA, or it could be BSB. Or if at all it is for an odd length palindrome, it has to be terminated with an A. Or it is an even length palindrome, it should be terminated with B. Or it is an even length, it is terminated with an epsilon characters. Odd length or an even length, it has to be terminated with A or B. So this is how you should be able to write a context-free grammars for a palindrome. So if at all we take an example of S tends to, you want to generate a parse tree in order to validate whether it is correct or not. A, B, B, A only will take. So the first rule that we are going to be generating is S. So for the first rule, it is S tends to A, yes, A, and B tends to B, yes, B. First rule I have taken here, second rule I have taken here, and then the third rule, it is S tends to epsilon. So it is A, B, 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 A, B, B, A. So it is A, B, B, A will be accepted. A, B, B, A. So this is a similar fashion. You can either validate your grammar using a parse tree, or you should be able to validate using this kind of a derivations. So here is one example, B, A, B. So you have to first derive with the second rule, that is B, S, B. And then it is A now next, it is A, S, B next. and then once again it is B. So you are going to be terminating with a B character. So this is the odd length palindrome string. This is an even length palindrome strings. Both the ways, if you can able to do the validation, both are correct. Similar fashions, we can also see that few more examples, that is equal numbers of A's and B's. How we should be able to generate grammars for equal number of A's and B's. Just now we have seen like equal length of A's and B's means it is A power n and B power n, it is ASB. So if at all it is starting with A means it is ASB. If at all it is starting with B means it is BSA. For one A, one B is there. For one B, one A is there. Ma'am, why is this particular SSB is used? If at all you want to have a palindrome series like A, B, B, A. This kind of a pattern, if at all you want to get it, which is having equal length of A's and B's only. So at this particular moment, you need to have SS, so that ASB and once again BSA. If at all you take, you will be able to get a palindrome as well. So this is SS is required. So in order to have a palindrome string, you should be able to have a SS pattern. So this is the equal number of A's and B's. Similar fashion, equal number of A's and B's, it is ASB, BSA or SS epsilon or epsilon. Ega, we will see one more example of more A's than B's. So this is a very simple way of doing it. So how we should be able to do more number of A's means, first let us write the conditions of equal length of A's and B's. So here you can see the grammar for ninth one, more number of A's and B's. For more number of A's and B's, how we should be able to write is, first let us write the grammar for equal length of A's and B's. Equal length of A's and B's is ASB, BSA, SS. And if at all we want to have more number of A's means one A would be terminated. And also we should have one more condition wherein more number of A's. So A, S, B, S. So this is A and this is B and this is A. So all the conditions of where the A is greater than B would be generated in this case. So it is a terminator is A and this condition. So this would generate you the more number of A's compared to the B's. Similar fashions, we have an example for a balanced parenthesis. Balanced parenthesis is also similar fashions. One opening parenthesis, one closing parenthesis. So recursively it is going to be generating. Say suppose you want to have multiple parenthesis option like this. So then SS is required. So it is like if at all you want to do the derivations of one open and closing parenthesis, one open, open, closing, closing, then it is first derivation is S tends to SS and then S tends to S, okay, and then S tends to open S closing, once again open S closing. So this is how you should be able to do the derivations for a balanced parenthesis, and it's very important from the examination point of view. Similar fashions, we have a language of 0 power I, 1 power j, I not equal to j. So this one, how we should be able to write a grammar is, it is equal length of, first we have to write, for this kind of a condition, first we have to write S tends to 0, S1. Okay, this will generate equal length of zeros and ones. But we should ensure that I is not equal to j. Then what I will do is that I am going to be introducing one A extra or one B extra. One B extra. It is or one B extra. And then what I will do is a 0 as 1, which will generate equal length of zeros and ones, and 1 A extra, 1 B extra. What it is going to be doing is that A will generate more number of zeros, okay, or at least one extra zero. B will generate more number of ones, at least one B extra it is going to be generating. So whenever you are going to be terminating this one, this is going to be generating more number of either zeros or less number of B's, or more number of B's or less number of zeros. So this is how you should be able to see. So or else you can also write a grammar like this, A or B tends to A or B, wherein first it will generate equal length of zeros and ones, 0 followed by ones, and then it will generate more number of zeros for A. For B also it will generate equal number of zeros and ones and more number of ones in this particular scenarios. And later the validation is the same process. Validation process would remain the same. Similar fashions, we will see few more examples. The few more examples on this is, we have Okay, 0 power I, 1 power j, 2 power k, wherein I is equal to j plus k. Okay, so in this case, it is I, 0. The 0 power is equal to j plus k. So whatever the power of 1, whatever the power of 2, that should be the total count of zeros that should be appearing. So here it is like, you have two ones and two twos, then it is two twos, 2, then it is 1 to the power of 2, 2 to the power of 2, it is 4 zeros should be coming, 4 zeros should be coming. For 4 zeros, 2 ones like this. So how we should be able to generate this one is, it is 0s2, the 0 should be associated with 2. How much ever 0 comes, so much 2 should also come. How much ever 0 comes, so much of 2 should also come. And then it is 0s2 and a tends to 0a1. So we will take a grammar. We will see that how we should be able to validate this one is, how we can validate this one is. So we can use like this. First one, if at all we want to generate 4 zeros followed by 1 ones, 2 twos. So it is s tends to 0, yes 2. First grammar, first one, first rule. Similar fashion, s tends to 0, s2. Similar fashion, s tends to 0, s. It is a. We need to take it as a. Now it is 0, s2 is done. Now it should be a. Now it is a. A tends to 0, a, 1. Similar fashion, a tends to 0, a, 1 and substitute epsilon character for this one. Substitute the epsilon character for a. So it is 4 zeros followed by 1, 1 and 2, 2. So you can see this 0, 0, 0, 4 zeros followed by 1, 1, 2 ones and followed by 2 twos. So this is how you should be able to generate a grammars for this one. So this could be a combinations. It can, j could be equal to I plus k. Okay, or k should be equal to I plus j. So we have a problem here. So on the similar ground, we have a problem like this. 0 to the power of I, 1 to the power of j, 2 to the power of k. J is equal to I plus k. Now this will be a concatenation. So it is like j is the combinations like 0, 1 and 1, 2. So it is a into b. It is 0, a, 1 and b is equal to 1, b, 2. So because j is a combinations of I and k, I plus k. J is an addition of I display. So 1 should be common here. 1 should be common. And here in this case, it is 0. So 0 should be common in this one. Similar fashions you have on the similar ground, you have k is equal to I plus j means it is what? 2. K is 2. 2 should be the repeated one. 0 s2 and s tends to a tends to 1e2. So this is how you should be able to